Hello friends, we are discussing methods of measurement of high current. From this lecture, we'll be covering the topic measurement of high current. There are different currents classified as DC current, AC current, and impulse current. These currents are to be measured for the purpose of some applications. Let us start with this methods of measurement of high current. You can check this particular slide. This shows the type of current which are mentioned on the left hand side, that is DC current. This DC current can be measured by three of the methods: resistive shunt with millivoltmeter, Hall effect generator, and magnetic link. The AC current that can be measured by two of the methods: resistive shunt and current transformer. Those current transformers are called as electromagnetic current transformer, as it works on the electromagnetic energy. Third is the impulse current, that is also referred as high frequency high current. There are four methods to measure the current: as resistive shunt, Rogowski coil, which is also referred as magnetic potentiometer, magnetic link, and Hall effect generator. There are few of the methods which are common, like Hall effect. This particular method is used for the measurement of DC current as well as for impulse current. Magnetic link, that is another method which is also used for the DC current and impulse current measurement. Resistive shunt is the common method which is generally preferred for DC, AC, and impulse current. So the common methods are discussed once. That covers the discussion on all the types of or all the methods of the measurement of DC, AC, and impulse currents. So repetitively, those methods are not discussed. A single discussion, single lecture covers all the three measurements, or maybe both the type of current measurements, etc. So let us start with the first method. This measurement of high DC, AC, and impulse current. So we'll be starting with the first high DC measurement. But before that, let us understand what is the necessity of the measurement of high current. In case of power system, if a short circuit occurs, maybe of any kind, that increases the current tremendously. On that current, the equipments which are placed on the power system should have a withstand capability. So this rising current in the power system due to the short circuit has to be measured, or the withstandability of the equipments to be calculated, and therefore there is need to have the measurement. Rising current increases the temperature and hence the heat. So that needs the heat run test on the power equipments like conductors, cables, circuit breakers, which comes in contact with that high current. And therefore, it is to be tested. And for the testing purpose, the current is to be measured. Even there is a cause called a lightning discharge, that is external cause, or even the switching transients, which occurs in large magnitudes, maybe of impulse, or the switching currents which occurs. These are large magnitude of currents is to be measured again, as that the equipments which comes in contact with that has to have the withstandability for these high currents. So therefore, there is need to have the measurement of these currents. Let us start with the first method, measurement of high direct currents, that is DC current. In this, first we'll be discussing the resistive shunt with millivoltmeter. it indicates that there is a resistance used, but it is shunt connected with the voltmeter. But that voltmeter is of very low range, that is of millivoltmeter. For that purpose, you can refer the circuit which is given here, where R is the resistance in ohms. There is a connecting cable used. This connecting cable connects this particular terminal called as current terminal, and across that a voltmeter, that is millivoltmeter, is placed. So this millivoltmeter basically measures the voltage drop which occurs across the resistance. So these are the two terminals across which the voltmeter is connected, and that measures the value of the voltage. There is a high current which is indicated as I, which passes through this resistance R. So here in another figure you can see there are two terminals shown, C, C. That indicates the terminals for current. Then here we have P, P. That indicates the terminals for voltage. It means across which we are getting the voltage. And that voltage is measured across the resistance, which is in ohms. So let us start with the understanding. High magnitude direct currents are measured using the resistive shunt of low ohmic value. The voltage drop across the resistance is measured with the help of millivoltmeter. It means the range of that voltage is very low, and therefore it is more than sufficient to have that much of voltage measurement. The value of the resistance varies generally between 10 micro ohms to 30 milliohms. So the range of resistance is very low. It is 10 to 13 micro ohms to milliohms. This depends on the heating effect and the loading permitted in the circuit. High current resistors means the selection of the value of the resistance depends on this. Now, high current resistors are generally oil immersed. These resistors are placed in the oil because oil acts as a medium called coolant. This oil is made up of, that is, this particular circuit is made up of 3 or 4 terminal resistances that you can see in the figure. If there are 4 terminals, that is CC be the terminals of current and PP be the terminals of voltage. This voltage drop across the shunt is limited to a few millivolts, which is less than 1 volt in the power circuit. And therefore, the name given to this particular method is the resistive shunt with millivoltmeter. So whatever the value of high current passes through this particular circuit, when it passes through that low value of the resistance, whatever the voltage drop occurs across that resistance, it is measured with the help of a voltmeter. But as this particular current value is very high, and therefore there is need to use the connecting cable. And this cable basically protects the voltmeter which is placed there. So this method is called as the resistive shunt with millivoltmeter. There is another method called as Hall generator. The principle which is used in this case is the Hall effect. So you can see a diagram. In this case, this shows a particular piece of metal and a flux density, magnetic flux density, is perpendicular to it. The width of that plate, that is the thickness of that plate, is small d. A current passes through, that current is DC current, passes through this plate. When this current passes through that plate, experiencing a flux density, it develops a Hall voltage. And this Hall voltage, it is in terms of the DC current, is the measurement of the DC current. Here, let us understand the principle of Hall effect first. As I explained already, if an electric current, that is small I, flows through a metal plate, that metal plate is already shown here, whose width is d, that is thickness is small d. So when current I passes through this metal plate located in a magnetic field, means it is placed in a magnetic field perpendicular to it, the Lorentz forces will deflect the electrons. So whatever the forces get developed, that deflects the electrons in the metal structure in a direction normal to the direction of both the current and the flux density, that is magnetic field. So this is what the principle which is used, called as Hall effect. Now, this is referred as Hall generator because in this case, the Hall effect is used to generate the voltage, and therefore it is named as a Hall generator. The charge displacement, as the electrons get deflected, so therefore the charge displacement generates an voltage or generates an EMF in the normal direction, and that voltage is called as Hall voltage, which is represented as VH. This VH can be given by the equation as this Hall voltage depends on, the flux density, the amount of current passing through it, the plate thickness, etc. And therefore, it is given by the equation VH is equal to R multiplied by B multiplied by I by D, where VH stands for Hall voltage, B stands for flux density, I stands for the current which is passing through it, D be the thickness of the plate, and R be the proportionality constant. That proportionality constant is called as a Hall voltage constant. That is, Hall voltage is proportional to the current I and flux density, and it is reciprocal to the plate thickness D. This proportionality constant R is referred as Hall coefficient. So this is what the equation which is generally preferred, and that decides the value of the current measurement. So whatever the current, DC current, is to be measured, that passes through this particular metal plate, so that in terms of Hall voltage that can be measured. This Hall coefficient for metal is very small, and generally semiconductor material is preferred, and therefore the value of that Hall coefficient is high. This Hall coefficient also depends on few of the parameters like temperature, magnetic field strength, that is H, etc. So the researcher has to keep this point in mind, that the Hall coefficient, which in this case is represented as capital R, depends on the temperature and the field strength, that is H. So this is what the principle which is required. Now let us understand the construction and the operation of this Hall generator. This is the way through which the flux density can be developed. There is an air gap in between the iron cored magnet. This is called as magnet because it experiences a flux, magnetic flux. So therefore, the material which is used is iron. The material is referred as core, and it has a current and hence flux therefore called as magnet. There is a conductor placed. That conductor experiences a flow of current. In between that, there is an air gap, and an Hall element, that is this metal plate, is placed here. So this is that metal plate which is placed. This metal plate is having a DC current, that is constant current flowing, that passes through due to the application of the DC voltage. There is a resistance used to control the amount of current. The thickness of this Hall element, as already said, it is small d. So this is what the Hall element having a thickness of small d. So what this figure shows, that shows the large current measurement arrangement. The current I carrying conductor is surrounded by an iron cored magnetic circuit. So there is a flow of current through this conductor which is surrounded by the iron core magnetic circuit, so that the magnetic field intensity H is produced in a small air gap. So in between the small air gap, like a flux density, there is a development of field intensity. So as we know, flux density is directly proportional to field intensity. The Hall element is placed in that air gap. The thickness of that is of small d. And there is a small current, DC current, named as ID, passes through that element. And hence, from the force, that is Lorentz force, develops the movement, Lorentz develops the force, or Lorentz force get developed there, that moves the electrons, and hence the charges get developed. Those charges are represented as what? The voltage. That is, voltage get developed, and that is developed across the Hall element in the normal direction, and that is proportional to the DC current that is to be measured. Now, what is the equation for that Hall voltage, which is already said? It is R into B into small I divided by small d. So this way, the measurement of Hall voltage and hence the DC current can be done. So this is what the second method. So this is what the second method which we discussed, called as Hall generator. Let us discuss the last method of the DC current measurement, called as magnetic link. These are used for the measurement of DC, as I said, also used for peak magnitude of currents, which passes through a respective conductor. These links consist of a small number of short steel strips on high retentivity. The two or more links, instead of having single link, if the two or more links are used and it is mounted at a particular distance, that is known distance, from the current carrying conductor, that can have more effect. It has been found that through experiments, the remnant magnetism of the link after impulse current of say 0.5 to 5 microsecond shape passes through that conductor is same as that caused by the direct current. And therefore, as I said, this magnetic link can be preferred for the measurement of impulse current as well as direct current. But the limitation to this impulse current is that shape of that impulse current must be of 0.5 to 5 microsecond. That is 0.5 of increase and 5 microsecond to of 50% decrease. Measurement of the remanence possessed by this link after DC or impulse current has passed through the conductor enables to calculate the DC or peak value of the current. Why this method is preferred? Because of the simplicity, the method has been used for the measurement of lightning current, that is impulse current, on transmission towers. It doesn't give information. Yes, there is a disadvantage. It doesn't give the information regarding the wave shape. For this purpose, an instrument called a fulcronograph has been developed, which consists of an aluminum wheel round rim, of which are slots containing magnetic links of sufficient length to project on both sides of the wheel. As the wheel is rotated, the links pass successively through a pair of narrow coils through which flows the current to be measured. The current at the instant during which a particular link traverses the coil can be determined by a subsequent measurement of the residual flux in the link, and therefore a curve relating the variation of the current with time can be obtained. The time scale is governed by the speed of rotation of the wheel in pulchronograph. So this is what all the information about the DC current measurement, where there are three methods used, and these three methods are helpful for the measurement of DC high current. So that's all with this lecture. Hopefully you all have understood the concept of DC current measurement. We'll see the measurement of AC current and impulse current in respective lectures, in next lectures. So thank you so much, guys. Take care.